And so today's topic is that we will start to discuss group theory and symmetries in physics. So in general, symmetries and group theory, which is the natural language to describe it, it's a very powerful tool, and it's very useful in formulating different physical theories. We've already seen through Noether's theorem that certain symmetries lead to conserved quantities. And also, if you go further, you can, based on the symmetries of a system, you can often deduce properties that the solution might have. I mean, you might be familiar with the fact that rotational symmetry, for example, in the case of electrostatics, means that the electric field needs to be pointing radially away from the source, for a point source, or for a general spherically symmetric source. So that can help us to deduce what the electrical field actually is in that case. So let's start by asking the question, what is a symmetry? So before we do that, let me also say that I am starting to make the lecture notes for these lectures, and I will put them up also as well on the Canvas page as soon as they are done. So what is a symmetry? Well, a symmetry of a physical system is any kind of transformation really that leaves the system invariant. So what I'm going to just say is that it's a transformation that leaves a system invariant. So what do we mean by that? Well, that before and after the transformation, the properties of the system should be the same. So for example, if I have a mass density before and after that, if that mass density has a symmetry, before and after the transformation, that mass density should be the same. So just to take an example of that, let's consider the following. So let's take an infinite wire. I mean, I cannot draw an infinite wire, but let's imagine something like that, and that continues on for infinity in both directions. And let's assume that it has some constant mass density per length. What kind of symmetries do we have here? Anyone wants to have a guess?
Rotation along an axis that goes through the wire.
Yeah, so that's one of them. So let me just draw that we can have rotations around the axis through the wire. This is rotations. Any other transformations that we can do? So
Does stretching count?
Stretching does not count, because if we stretch it, the density per unit length will decrease, right?
Right.
A priori. So I'm thinking now in terms of rotations, translations, and reflections. So what we have in addition here is that we can make translations in the y direction, right? If the wire is infinite, it will still occupy the same space. We can also make reflections in a plane here. Well, I can choose whatever plane along the wire, as long as it's perpendicular to the wire. If I make a reflection, it will look the same before and after. These are reflections that I can a priori move back and forth. There is another, so if we look at rotations and translations, they are both continuous symmetries, because we can rotate by any amount and we can translate by any amount, while the reflection is a so-called discrete symmetry. We can only make a reflection and a reflection again. We cannot make a half a reflection. There is one more discrete symmetry, which kind of reminds of the reflections, but it's a priori physically different. I'm running out of colors here. Let's take orange. As if we have rotations around an axis that is perpendicular to this wire, then we can make pi rotations. So, of course, an arbitrary rotation here will not map the wire to itself, so to say. However, if you make a half turn, then that will map the wire to itself. So that is a symmetry here. Now, another concept that we will encounter is so-called symmetry breaking. So, for example, if I push an electrical current through this wire, then not all of these symmetries are preserved. So, for example, reflections, well, actually both of these discrete symmetries are going to change the direction of the current. So if I add this current through the wire, both reflections and pi rotations are going to go away as symmetries, and we will be left only with the translations and the rotations. Questions so far? Okay. So what we discussed here now was physical, like rotations and translation, but the transformation does not, or symmetry in general, does not need to be like a physical rotation. It can also be some sort of transformation of your variables such that the situation is the same. So it does not need, oops, I should remove that, not need to be a physical, to be a spatial symmetry transformation. For example, if we look at Maxwell's equations in vacuum, then they take the following form. So the divergence of the electric field and the divergence of the magnetic field are both 0. And we also have the following expressions for the curls. So the curl of the electric field plus the time derivative of the magnetic field should be 0, and that should also be the case for the curl of the magnetic field minus 1 over c squared times the time derivative of the electric field. Now, in this case, we can make a transformation between the electric and magnetic fields. So I could define the following. I could define the electric field could go to a new E prime, such that this E prime is given by cosine alpha times E plus sine alpha C times B. If I at the same time let B go to B prime, which I define as minus sine alpha E over C plus cosine alpha B, then the Maxwell equations in vacuum will be true also for E prime and B prime. So this is a symmetry of Maxwell's equations. I mean, there's nothing spatial going on here. I'm not rotating the E field. I'm not rotating the B field. I'm making a rotation from the E field to the B field. I'm making a change in what I call the E field and what I call the B field. But these new fields also satisfy Maxwell's equations. So that's an example of a different symmetry. So let's go to the maths. How are we going to describe this symmetry? Well, we're going to use what is called group theory. And as we will see, this is kind of the natural language in which we can express symmetries. And today I'm going to go through a lot of kind of definitions in group theory. And later on, we're going to see examples of groups, and we're also going to see how we can apply those examples to different physical systems. So let's start. Let's start by making an observation here. So we note that if we combine two symmetries, the combination of two symmetries is a new symmetry. For example, if we look at the case of this wire, if I make a translation and then I make a rotation, I mean, I'm still keeping the mass density here of this wire invariant under those transformations. However, this translation after and then a rotation, if you combine them, it's sort of translation plus rotation, but it's still a symmetry. It's not a pure translation, it's not a pure rotation, it's translation plus rotation. If you wanted to make it continuously, it's like translating and turning like in a helix. So the combination of two symmetries is a new symmetry, and this is exactly the property that we're going to look at for groups. So let's start by defining what a group is. Oops. So definitions. So a group G is a set of objects in our case it's going to be symmetries such that or with a binary operation, or which is called the group operation, that takes two elements, because it's binary, from the group and maps them to a third element. That maps two elements in G to a new element. And it also needs to satisfy the following criteria. So before we go through the criteria, let me just discuss the notation that we're going to use. So in general, you would take, if you have A and B as elements of this group, then there are many different possible ways of denoting this group operation. And it might depend on what kind of group you're looking at. So for example, you might use plus, you might use a star, you might use a small dot, or you just simply might write the group elements after each other. So what I'm going to do, as long as we're talking theoretical things, I'm going to just put the group elements after each other. And when I do that, it means that I'm taking the group operation between those elements. So the first condition is the closure condition. And essentially, I already said this. So this means that if we have both A and B as elements of this group, then if I take the group operation, which I will often call A multiplied by B or A times B, this group operation, this binary operation gives back a group element. So if you take the group operation between two group elements, you get back a group element. So this is exactly the same kind of statement that we had up here for symmetries, that if we do one symmetry transformation and then do another, we end up with yet another symmetry transformation. So that's the first condition. The second condition is that the group should have an identity element. So this means that there should exist an element E in G, which has the property that that if you take that for all for all elements in G, you should have that EA should be equals to AE should be equal to to A. So this is the identity. If you look at physical transformations, this identity is going to be do nothing, because a physical system is always invariant under the do nothing. So map everything to itself, and all the properties are going to be invariant under this. And if we look at this condition, it just says that if you do nothing and then you do the transformation A, that's the same as doing the transformation A. Or if you first do A and then do nothing, that's also the same as just doing A. And note here that when we're looking at the order of transformations, typically we are reading it from right to left. So when I'm looking at things like AB, it means when we apply it to physical transformation, it's going to mean first do B, then do A. So that's the identity. The third requirement is that there should exist an inverse. So for any A, for any A in the group, there should exist an inverse. But I'm going to denote A to the power of -1. That's also an element of G. So this means that A inverse is equal to A inverse A, which is equal to the identity element. So this is also kind of, we look back to the physical transformations, this means that I should be able to undo the transformation. For example, if I look at the translations here, I can first translate by a fixed amount in one direction, and the inverse of that transformation is translating by the same amount in the other direction. And then I get back to the original system. The same for rotations or for reflections. And finally, the fourth is associativity. And so this means that, so for A, B, and C as group elements, then I want to have that A, B, C should be equal to A, B, C. So I can define it as A, B, C. So this means that if I take first the transformation, which is the composition of B and C, I do that first, and then I do the transformation A. That should be the same thing as first doing C, and then doing the transformation that is the combination of A and B. Of course, when I'm talking about transformation, it's quite intuitive that this is the case, because this A, B, C here just means first do C, then do B, then do A, which becomes exactly the same thing as this. Any questions so far? Okay. So let me note that one thing that I did not discuss now, or in particular one property that we did not have, but that will be the case in many situations, is commutativity. So commutativity is not a requirement for this group operation. So what we're going to discuss now is called abelian groups. So an abelian group is a group where you have commutativity. So if AB is equal to BA for all A and B in the group, then we say that the group is abelian. Or that the operation is commutative, because AB is equal to BA. Conversely, if this is not the case, we call the group non-abelian, which means that not all elements commute with each other. So, for example, if you look at, if we look again at this wire, it is a non-abelian group because making a translation and then a rotation is not the same as making a rotation and then the translation. However, if you look at subgroups here, so if you just look at translations, all translations here commute with each other. And the rotations as well commute with each other. So as I said, this is a lot of definitions now, but we'll have to live with that because later we're going to see how this carries on to physics. And we will see some examples of particular symmetry groups that we will look at. So the next property that I wanted to discuss is so-called conjugacy classes. So what we can do is to define a relation between elements that is called conjugacy, or that the elements are conjugate to each other. So if we have two elements of a group, so A and B belong to a group G, we say that they are conjugate. We write that as A similar to B if the following is true. So if G A G inverse is equal to B for some element in the group. So this means that if you essentially if you have a transformation G that transforms between those two, then those two elements are conjugates. So you can see it as physically being kind of similar. So for example, if we look at rotations in 3 dimensions, that's typically, or it's always a rotation around an axis of rotation, right? So if I take that axis of rotation and I rotate it, so well, let me actually draw that. So let me draw the following. If I have an axis of rotation here, so I have a rotation around that axis, and I have another rotation but a different axis, then, and those rotations are both, say, by pi thirds. So this is a pi over 3 rotation, and this is a pi over 3 rotations. Those two are going to be conjugate to each other, and the transformation that takes them to each other is going to be a rotation that rotates one axis into the other. So I'm going to have a rotation here. Let me take this. I'm going to have a rotation that moves the green axis to the red axis. So doing the green transformation is the same thing as first rotating the green axis to the red axis with some rotation G or G inverse, then doing the red rotation and then rotating back. So in essence here, this would be G inverse, and rotating back would be G. Now, this is an equivalence relation. And what does that mean? So conjugacy is an equivalence relation. So that means that, first of all, A is always conjugate to A. So every element is conjugate to itself. It's rather simple to see. You just take, in this definition here, take G equals to the identity element. So then you say that A is equal to A, which is true. And so this is true for some G. So A is conjugate to itself. We also have that if A is conjugate to B, then this means also that B is conjugate to A. So this is symmetric. We can see that if we just multiply here by G from the right and G inverse from the left, that we will have the same kind of relation, just with the rows of G and G inverse reversed. And finally, if A is conjugate to B and B is conjugate to C, then A is conjugate to C as well. So these are the requirements for being an equivalence relation. And this means that you can sort all of the group elements into so-called conjugacy classes or equivalency classes. So all group elements can be sorted into conjugacy classes. For example, then, in the case of three-dimensional rotations, I can sort all the rotations into the conjugacy classes will be rotations of a fixed angle. So all rotations by an angle pi third will be conjugate to each other. Those form one conjugacy class. Another conjugacy class will be all rotations by an angle pi half. Any questions about that? Because this is a rather abstract concept.
Would you mind explaining the last sentence again?
About conjugacy classes.
Yes.
Yeah. So I mean, conjugacy classes are elements in the group that are similar in some sense. So, for example, here in the case of three-dimensional rotations, we're going to find that all rotations that are rotations by the same angle are conjugate to each other. Essentially, because we can make a transform. You can transform those rotations into each other by other rotations, let's say. Let's take an example also and let's look at the conjugacy for the identity element. So the identity element. So E. We're going to see that the identity is only conjugate to itself because no other transformation is doing nothing. So if we look at that, so assume that A, which is an element in G, is conjugate to E. So it's conjugate to the identity. In order for that to be true, we must have that GE times G inverse is equal to A, because this is the definition of being conjugate. However, if I look at this first expression, so I'm looking at this now. The identity times anything is that anything. So in particular, if I look at G times E, That's G. And I still have G inverse. And I can choose which order I make those multiplications here because it's associative. However, we know that G inverse per definition is E. So we now have that A is equal to E. So the only element of the group which is conjugate to the identity is the identity itself. If you look at it in terms of transformations, the only transformation that is doing nothing, so that's the conjugacy class of the identity, transformations that do nothing, is the transformation that does nothing, which is the identity element. Other questions? Okay, so we have 3 more rather quick definitions to go through, and then we'll have a break. So the first of those is the concept of subgroups. So it's not really anything strange, it's just that a subgroup called H of the group G is a subset of G. Such that all group axioms are satisfied for H. So in particular, the subgroup must contain the identity element. So E must be an element of H. It must also be the case that it's closed. So the closure must be true. So if A and B are elements of H, then that must imply that AB is also an element of H. And finally, the inverse must also be in H. So if A belongs to H, that means that A inverse also belongs to H. Now the fourth group axiom is automatically satisfied because we already know that this group operation that we have in G is associative because G is a group. So we don't really need to check that explicitly. What we need to check explicitly is that those 3 things hold. In particular, I mean, the identity always needs to be an element of H. That's not very difficult to check usually. But we need to check that this subgroup is closed and that also the inverse belongs to the same subgroup. If we look at examples of this, well, let's go back to when we discussed symmetries in the beginning. We had this wire here. And so the wire in general had these translations, rotations, and if I put a current through it, we did not have these reflections and pi rotations. But if I look at these translations and rotations, translations and rotations generally form a group. However, both translations and rotations by themselves form subgroups of this group. So if I just look at translations, of this wire back and forth, it's a separate group. It's a subgroup of this group of translations and rotations, because doing nothing, well, that's a subgroup of translations. It's a part of translations. It's a translation by 0. Doing one translation and then doing another translation is also a translation. And finally, the inverse of a translation is also a translation. Just translate by the same amount in the opposite direction. So translations indeed is a subgroup of translations plus rotations. The same is true for rotations in this case. It can also be like discrete things. So if we take this as an example, let's look at the following figure. So let's make a triangle. Oops, it's supposed to be an equilateral triangle. If we imagine that this is an equilateral triangle with directed sides, this is not an invariant under any rotation, but it is going to be invariant by rotations by 2 pi over 3, because rotations by 2 pi over 3 are going to map this triangle into itself with the same directions of the sides. So rotations by 2 pi over 3 is a subgroup of continuous rotations, for example. Right, any questions on subgroups? Okay, so a related concept to subgroups is symmetry breaking. So symmetry breaking occurs whenever you have a symmetry group of some physical system, and then you do something to that physical system such that the remaining symmetry is only a subgroup. So it's when a symmetry of a system is broken to a subgroup of the symmetry group. An example of that, let's again go back to the wire. An example is exactly what we did here in the beginning. We had a wire, and without this current, the wire had all of these symmetry. It had translations, rotations, reflections, and pi rotations. But as soon as I introduce this current, I break that symmetry to the subgroup of translations and rotations. So no longer are those reflections and pi rotations the symmetry of the wire. So that's symmetry breaking. I broke it to the group that only consists of translations and rotations and their combinations. So that's just a piece of nomenclature. Finally, the last 6 minutes of this hour, I want to discuss so-called homomorphisms. So in short, homomorphisms are maps between two groups that preserve the group structures. So, oops, that's the formal kind of description. Maps that preserve maps between the groups. That preserve the group structure. So let's take two groups. Let's call them G1 and G2. A homomorphism between those two groups, let's call it ρ. It is a map from G1 to G2 such that if you take ρ for any two elements A and B that are typically elements that are elements in G1, if you take ρ and you apply it to the product, what you get is the product of ρ acting on A and B separately. So this is just telling us that it doesn't matter if we first multiply A and B and then apply this transformation, or if we first apply the transformations, so take row of A and row of B separately and then multiply them in G2. So just, I mean, the kind of most basic example of, well, there are two kind of basic examples that we can discuss. The first one is called the trivial homomorphism. So the trivial homomorphism, which is just saying that for any element in G1, map that element to the identity of G2, because then that's automatically going to satisfy this, because row of anything is identity. So what it says here is that the identity times the identity is the identity, which is trivially true. So this is the trivial homomorphism. We can also look at the trivial automorphism, which is just, you can make a map, a homomorphism from a group to itself. So if G1 is equal to G2, so if G1 is equal to G2, you can always take row of A equal to A, and that's obviously going to satisfy this criterion as well. And finally, just a small note of nomenclature. I'm going to put it in red, so comment. A homomorphism with an inverse is called an isomorphism. So having an inverse means, it means that it must be a bijection. So this trivial homomorphism in general, unless we're looking at a trivial group with only the identity element, this cannot be an isomorphism. But we must map all elements in G1 to separate elements of G2. Okay, I hope everybody's back. So last hour, we introduced groups and symmetries. So this hour, I'm going to spend on discussing a certain class of groups called discrete groups. And then next lecture in this course, that is only for this course, I will start discussing continuous groups. And so for the remainder of this hour, I will first discuss discrete groups in general, and then I will discuss some of the examples of this. So the topic of this hour is discrete groups. So if we remember from last hour, we started over here. We started by looking at this wire. This wire is a very good example of things that we can look at. So we looked at different kinds of transformations here. We looked at translations and rotations, and common for both of those is that you can do half a rotation, you can do half a translation, you can do a translation, and you can do that translation times pi if you want to. So those are continuous symmetries of a system. On the contrary, reflections and these rotations by some fixed angle, in this case pi, they are discrete symmetries. You can't do half a reflection, and you can't do half a rotation, half a pi rotation, because it will no longer be a pi rotation. So it will, in this case, no longer be a symmetry of this wire. So with that in mind, let's discuss what is characteristic for a discrete group. So a discrete group the way we're going to define it has a countable but possibly infinite doesn't have to be infinite, but it can be number of elements. So that means that, for example, translations is not a discrete group because you can make translations by any amount, by any real number, and real numbers are not countable. On the other hand, if you limit to translations by some fixed amount or multiples of that amount, that is a discrete group because it is countable. You can translate by 1, 2, 3, 4, and so on. So that's going to be our example later on, but first let me discuss a little bit more about the discrete groups in general. And we say that a discrete group can be constructed from a set of generators. I'm going to write that those generators GI together with their inverses and in addition a number of relations between them. So in order to define a discrete group, I can just say I have these generators, these group elements in my group, and the relationship between those group elements are the following. Let's also say that if a group can be constructed with a finite number of generators, then it is said to be finitely generated. Also, we can talk about the finite discrete group if the number of elements is finite as well. So, as I alluded to, our example is going to be finite translations. So if I take now, if I just look in one dimension, the spatial transformation in one dimension is going to be limited to just translations and reflections. And if I look at the long chain here, so let me draw a line. That's my one dimension, and then I'm going to draw. Going to say that on this line I have a number of points. It can be just some there might be some masses there that are connected with springs or whatever, but I'm just going to consider the symmetry here, and this continues for infinity. So we are repeating this pattern in both the positive and the negative direction for all eternity. Then if I introduce here the symmetries of this system, I have translations by this distance between the points, if we call this L, then translations by a multiple of L is going to be a symmetry of the system. So I'm going to have these translations by a distance L. Those are a symmetry of the system, but also translations by 2L, 3L, and so on are symmetries of the system. But I also have the possibility of making reflections here. So if I take a reflection, I can call it sigma. I'm going to call this sigma 0 because if I put x equal to 0 here, then it's the reflection around 0. But I can also have other reflections. For example, I could have the reflection about this point, which would be sigma minus 2/2 L, because it's a reflection around the point minus 2/2 L. And those are all symmetries of this system. If I want to write down the generators of this symmetry group, it's actually enough if I consider just sigma 0 and the translations by L. So those two transformations are going to generate this symmetry group. So the generators are going to be TL and sigma 0. Now, the relations that we were talking about that define this group, along with the generators, is that, first of all, any reflection is its own inverse. So that means that sigma 0 squared, which is defined just as sigma 0 multiplied by itself, should be the identity element. So if I do a reflection and then I do the reflection again, I get back to the same situation. But I also have a relation with the generator of translations. So I'm going to have the following relation, that TL sigma 0, TL sigma 0, that's also equal to the identity element. So in order to see that that is actually the case, let's actually look at what's going on. So I'm going to just mark a number of points here, and then we're going to see what the symmetry transformation does to these. Again, consider them continuing for all eternity in both directions. So if I take these points, and for the sake of it, I'm going to mark one point green and another one pink, just to see what's happened to them under these transformations. And I'm going to put x equal to 0 around here, so that we know what's going on. So did I copy that? Yes, I did. Very good. If we take first, if we look at what's going on when we do this first transformation. So the first thing that we did, and let me now just mark x equal to 0. The first thing that we did, or that we do in this operation, going from the right now, is that we're going to make a reflection around x equal to 0. So that means that, well, the green point remains where it was, and the pink point jumps to the other side under this reflection. Okay, so that's the first thing we did. The second thing we do is that we make this translation TL. If we do that, the green point is translated from x equal to 0 to the next point, and it's the same for the purple point. So we end up with the green point is here, the purple point is there. The third thing we do is a reflection again around x equal to 0. which means that the purple point, which is at x equal to 0, is going to remain where it was. The green point is reflected to the other side. And we have one remaining transformation, which is to make a translation again. And that transformation is going to leave the purple point over here and the green point over here. So if we just write out what we did here, we first did this reflection, we then did the translation, then we did the reflection again, and then the translation again. So we did sigma 0, TL, sigma 0, TL, and as you can see, we end up here with the same set of points as we started with. So doing those transformations in this order ends up being the same as doing nothing, which is the identity transformation. So this relation must hold for the symmetry group. Any questions on that? Okay, so that about generating different discrete groups. We're going to see more examples later on. Just before we come to the examples, I want to discuss what is called Katy Tables.
Is it okay if I ask a question before?
Of course.
I was thinking that this reflection sigma, is it really discrete? Because we could choose any point. For instance, here we chose -2.5.
Yeah, but we cannot choose. So the point is we can choose the points themselves.
Yeah.
Or we can choose midpoints.
Yeah.
We can't choose a point that's there,
No?
for example, because that would map this point there.
And that wouldn't be a symmetry.
And that wouldn't be a symmetry because you would map the points to somewhere where they were not from the beginning.
Okay, thank you.
Yeah. Right. And even in that case, they would, I mean, that reflection by itself would be discrete because you can't do half a reflection. So let's look at what's called Katy tables. And I mean, you essentially know this from elementary school because a Katy table is nothing but a multiplication table. So it's going to essentially tell you how well it's going to be a table representation for a finite group, because otherwise we would have to make an infinite table. So it's a representation of all of the group operations between different elements. So it's in essence, it's a multiplication table. And so what we do is that we do exactly the same thing as you do with multiplication tables. You make a table like this, and it's going to be, the size is going to be different depending on how many elements you have in your group. But let's just start like that. And then in the first row and the first column, we're going to place all of our group elements. And we're going to start with the identity. So we're going to write the identity here. And then we start writing the different group elements. Since it's a discrete group, it's countable. So I write A1, A2, A3, and so on. And I do the same thing in the first row, column, sorry. So A1, A2, A3, and so on. And then in all of the remaining squares, we write down the product or the result of the group operation between the element that is in the first column and the element that is in the first row. So for example, in this square, we're going to write A1 times A1. So that's A1 squared. In this square, we're going to write A1 times A2. And we're going to write the actual result. We're not going to write A1, A2. I will come to that later. And here A1, A3, and so on. So A2, A1, A2 squared, A3 squared, A2, A3, A3, A1, A3, A2, and so on. So this is a multiplication table. So just an example of that. Let's take a group which is called the cyclic group of order 3. So I'm going to come back to that, what that means later. But we take G is a group which contains the identity. It contains an element C, and it contains the inverse of C. And as it turns out, the inverse of C is going to be such that C squared is the inverse of C, which is equivalent to C to the third power being the identity element. If I wanted to make the group table here, I'm going to need a 3x3 table. I write E, I write C, and I can write C squared or C inverse. It's the same thing. So I start like this. And then here I have C squared. In the next, I have C multiplied by C squared. So I will have the identity there. The same is going to go for this element. I have C squared times C, which is C to the third. So that's the identity. And finally, I have C there. So that's about that. Note that this group is abelian. So everything commutes with everything. And since it's abelian, this table is going to be symmetric, because A2, A1, in that case, is equal to A1, A2, which means that it's symmetric under exchange of those. Another thing that we note is that each row and each column contains all elements. So this must be the case, otherwise it's impossible to, otherwise the inverse does not exist. So there is a number of statements that you can make about these Katy tables that result from the group axioms. If you're given a multiplication table, you can a priori check those things such that such as all of the elements appearing in each row and each column, and if they're not, you can say, well, this is not the multiplication table of a group. Or based on a Katy table like this, you can be asked the question: is this group abelian? And then you would check whether or not it's symmetric under transposition or not. Any questions on Katy tables? Okay, then let's get to examples of groups, or rather examples of discrete groups, as that is what we have been discussing. And all of the groups that I'm going to discuss now are going to have some sort of physical significance. You will find them like in chemistry discussing symmetries of different molecules and such things. Because if you know the symmetries, again, you will be able to draw certain conclusions about how that molecule interacts, or what its vibrational degrees of freedom can be like. So the first example is the cyclic group. which we denote by Cn. So this is a cyclic group with n elements. That means that we have a single generator, which I will call C. And that generator satisfies that C to the n is the identity. And this is isomorphic to rotations by 2 pi divided by n. So for example, if you remember this triangle with directed sides, the symmetry group of this triangle, seen as a two-dimensional figure, is C3, with 2 pi over 3 rotations being the generator of this. Another example I prepared a little bit here beforehand is this. If you consider this yin-yang symbol, and we consider also the case that let's disregard the colors. Let's say that we do a rotation and the flip of the colors. Then the symmetry group of this is C2. Because you do a rotation by pi and you flip the colors. The symmetry group is then going to be C2, because if you do that again, you end up with the same figure. If you have seen the roundabout road mark, it has a symmetry group which is C3. So the same one as this triangle, because it's 3 arrows pointing in some direction. And if you rotate it by 2 pi over 3, you get it back. So that's C3. Right. So this can be useful because it can be the symmetry group if you have, for example, now let's take that later on, actually. Let me move on to the dihedral group. Which I will denote dn. So this is rather similar to the cyclic group, actually. And it's going to be the cyclic group, just that we add an additional symmetry, which is a reflection symmetry. So we have 2 generators. We have this C generator that we had in the cyclic group as well, but we will also have a reflection generator. And the conditions that we put, or the relations between those, is that first of all, I want that the nth power of C, again, is the identity. This is the same relation as we had for the cyclic group. And since sigma is a reflection, if we do it twice, we get the same figure back, or the same. We get the identity. However, there is now an additional requirement here, which is that in addition to those 2 relations, I want that C sigma should also be the identity. I mean, you might recognize this essentially as the same relation as we had here for the finite translations. Just that in this case, we have an additional constraint on that generator. So it's not the same group as finite translations. This is a finite group because we have a finite number of elements, unlike the finite translations and reflections, which has an infinite number of elements because you can have any integer multiple of translations. So if we want to look at what this dihedral group is the symmetry group of, we can look at, for example, the triangle without directing the edges. So for this triangle, I still have these rotations by 2 pi over 3, but I can also add here a reflection in through a line that goes through one of the corners and one of the edges. And so this makes the symmetry group of this triangle the dihedral group. One thing to note here is that what we have done here is to look at figures in 2 dimensions. There are actually, if you look at these objects, so if you look at this triangle, for example, as a triangle in 3 dimensions, there are 2 possible ways to realize this reflection. One thing would be to just take the reflection in this plane perpendicular to the plane of the triangle that cuts the plane of the triangle in this line. However, the other possibility is to just make a pi rotation around that axis. So those are both possible ways of realizing this dihedral symmetry. And in 3 dimensions, you can have both of those, and those are different. So that is going to be a group that is called D and H instead. So how do you write it? So in 3D, we have additional symmetries. So, for example, two-dimensional reflections. So for example, this would give us the DNH group. Just to say a bit about that, just to take an example of that, let me do the following. So let me take this and let me try to draw something like this. So let me draw that. That's an oxygen molecule, oxygen atom. And I can take 2 hydrogen atoms, so you recognize this as the water molecule, right? The symmetry group of this water molecule is D2H, because what we can do is it's D2 actually, right? Because what we can do here is that we can make those reflections, and we can make pi rotations. So this would be C, and this would be sigma. Okay. Whereas, I mean, if I take something else, like the ozone molecule, so that would be something like this. It would be actually this triangle. What we could do here is that we have these rotations by 2 pi over 3. Then we have exactly the pi rotations around this axis, but we also have the reflections in this axis. So we would have 2 different transformations mapping the positions of these oxygen atoms to each other. Questions on those examples? Okay, so the last example I want to have today is what is called the symmetric group. It's denoted Sn. And it's a rather important group because it's going to turn out that this is that all of the groups that we just discussed are going to be subgroups of this group. And it's rather useful to know a little bit about this. So this symmetric group, so Sn, it is the group of all permutations of n elements. So if you're familiar with permutations, I mean, it's just if we have n elements, in how many different ways can we order them? So this then means that the number of different ways that we can order them, well, for the first element, there are n possibilities. For the second, there's n minus 1, then n minus 2, and so on. So the number of elements is n times n minus 1 times n minus 2 and so on, which is n factorial. So an element of Sn, that's some function which maps the current position of an object to its position after this permutation. So it's a function sigma from the elements 1 through n to the same elements 1 through n. And of course, the identity element is the identity function. It's just doing nothing. So it's mapping 1 to 1, 2 to 2, and so on. And it's relatively simple to also check that all of the group axioms are satisfied here. So I mean, you can do a permutation, and then you can do another permutation, and that results in a third permutation. So an example of this is S3. So this is the set of permutations of 3 elements, and an example of that is we have a function that maps 1 to 3. It maps 3 to 2, and the only remaining thing is that it also has then to map 2 to 1. Another possibility is that sigma maps 1 to 3, it maps 3 to 1, and it maps 2 to 2. So those are both elements of S3. When I have a cycle like this, so this is called a cycle. A cycle is a permutation of the form that we have 1 goes to sigma of 1, which, well, in general doesn't need to be 1. Let's take something else. Let's take A. So we have that A goes to sigma of A, which goes to sigma square of A, which goes to sigma to the n of A, which goes to A. So that after some finite number of applications of this permutation, we're going to get back to the original case. So the notation used for the elements of this symmetric group is that cycles are represented in the following manner, so that if I have exactly this cycle, a to sigma 2a, and so on, I would write a, then I would write sigma of a, and then sigma squared of a, and all the way up to sigma to the n of a. So this means that I know how this permutation acts on any of the numbers which are in this cycle. So for example, if I act on a, I know that the result is going to be sigma a. If I act on sigma n, I know that the result is going to be a. And in general, any element of Sn can be represented by disjoint cycles. That is to say, you can write it as a product of cycles that do not contain the same elements. So for example, yeah, let's take this guy here. We know that this transformation, well, it maps 1 to 3 and then 3 to 1. So that's a 2 cycle. This is a cycle of length 2. But it also maps 2 to itself. So that's a cycle with just one element. So in this case, these cycles are disjoint because this cycle does not contain any of the elements in that cycle and vice versa. So we can write any element in Sn as disjoint cycles. The question becomes, how can we multiply cycles together if they do have these common entries? So multiplication in Sn, well, of cycles, well, you can do it in the following way. So the first thing that you want to do is that you pick any number that you have not considered already. So pick a number not already considered. Two, you well, write it down first in first step. So write it down. And two is that you check what number the product maps it to. If it is a new number, write it down. Otherwise, well, and do 2 again. Otherwise, 3, you write parentheses around the cycle. So that's going to correspond to when you get back to the start of the cycle. Then we just write parentheses around the cycle, and repeat from 1. So I mean, this is going to be clear if we just take an example. So let's do that. So let's take the following 2 cycles. So multiplication of, let me take the same as I took in the notes, 1, 2, 3, and 1, 4, 3. Let me also say one thing here, that if we have something like this, so we have an element of Sn where we have a 1 cycle. That's rather uninteresting. So typically we would not write that out. Typically we would just write this as 1, 3. because it's the only things that we're changing. So if we get back to this multiplication here of the cycle 1, 2, 3 with the cycle 1, 4, 3, the first thing that we would do, so this is an element of S4. The first thing we do is that we choose a number which we have not already used. So a good choice is 1. So we choose 1. And the next step is to see what does 1 map to. And then we start on the right hand side here, and we let 1 go through these permutations. So first 1 maps to 4 due to the first cycle, and then 4 is not affected by the second cycle. So the product of those cycles is going to map 1 to 4. So we write 4 down. And the next step is then to look at where does 4 map. So if we take 4, we first see that the first cycle maps 4 to 3. And then the second cycle comes in and maps 3 to 1, which means that we are back at the start of this cycle. And according to what we just said here, that means that we should write parentheses around these, because that's a full cycle in the multiplication here. And then we return to 1, so we pick a number that we have not already looked at. In this case, a good choice is 2. 2 is unaffected by the first cycle in the product, but in the second it maps to 3. So we write the 3. And now since we've written everything, we could just as well just make these parentheses, but for the sake of it, let's just check that 3 maps to 2. So 3 maps to 1, which maps to 2. So we have finished the cycle. So what we have found out that this is actually this product, 1, 4, 3. And that's the kind of way that you have to do if you want to make multiplications of elements in SM. Let me just quickly go through. We have 1 minute left, and then there will, I will have some time for questions as well. Let me just make the note here that all of the groups that we looked at, so the groups CN, DN, and DNH, they are all subgroups of some SN. Doesn't have to be the same N here as the N there, but they are subgroups of some SN. For example, let's take the triangle as an example again. So we have this triangle, this equilateral triangle, or at least I'm trying to make an equilateral triangle. And then we look at the symmetry group here. So what we can do is that we can order those corners of the triangle and see what do the symmetries do to those. Well, we see that they permute those. So for example, if I take the rotation here by 2 pi over 3, it's going to map 1 to 2, it's going to map 2 to 3, and it's going to map 3 to 1. So that's just the element 1, 2, 3. So C is 1, 2, 3. It's just that cycle. If I look at the reflection instead, so let me look here at the reflection in that line and call it sigma. What that is doing is that it's keeping 1 fixed, but it's exchanging 2 and 3. So the sigma here is going to be the cycle 2, 3. And then you can generate the entire group, which was in this case D3, from those 2 elements as a subgroup then of this S3 in this case. Yeah, we're already 1 minute past. There is another example, and afterwards when I put these lecture notes online, you will see that the D6 is naturally in exactly the same fashion. It's a subgroup of S6. Yeah, that's about it for today. Are there any questions?
What does this multiplication even mean?
This multiplication of in Sn, you mean?
Yes.
Yeah, so it means making one permutation and then making the next permutation.
I see.
So the combination of making permutation after permutation is a new permutation. And that's all that we require from a group operation.
Okay, thank you.
So the group operation in this symmetric group is just do one permutation after the other.